Good afternoon, everyone. My name is Bernadett Spisák, and I would like to say a few more words about the simulation work we have been doing in my institute for applied research. It's called Simulation of Crack Propagation using the GTN ductile damage model based on the virtual crack closure technique. Before doing anything about what the simulations were done, I would like to say a few words about the background and the aim of the work. First of all, we are working with nuclear power plants, therefore it is related to this topic. There are quite a lot of reactors already operating all around the world. There are more than 400 of them, and most of them, at least half of them, are already over than 30 years old. Therefore, it is very important to have aging management in case of these reactor pressure vessels. For this, we need more information about the material properties of the equipment, and also we need some solution for this. One of them is to transfer the material properties from small scale to large scale components, and also the second one is to use miniaturized specimen. But for these results, we don't have standardized calculations which could be used. Therefore, our work is basically with the following content. First of all, we determine the GTN parameters, which is related to ductile behavior with anti-specimens, where we use artificial neutral network. Thereafter, we apply these parameters for 1T CT specimens to validate the results. Thereafter, we use the unloadings in case of the simulation. So with the standard method could be evaluated and the J delta curves could be determined. We compare them with the testing and they were showing quite good results. And finally, I will say a few words about what is the new thing about our calculation is the VCCT model, where we update it with our thoughts. So the first step is to determine the GTN parameters with the artificial neutral network. For this, we use small sliced notch tensile specimens. As it can be seen from the diagram, we use flat versions instead of the commonly used cylindrical versions because of the limited material we had. Therefore, we could save material with this method, and we wanted to show that even in case of flat specimens, we could determine GTN parameters. For this, we made 90 different simulations where we used the LH sampling method approach to randomly generate points in a defined domain. And here can be seen in the table what were the parameter ranges we used. It was based on the literature. And finally, we applied these simulation results into artificial neutral network, and we were able to generate the parameters with these simulations. And to validate the GTN parameters, we made 1T CT specimens, also made the simulations with them. And as it can be seen that results are quite in good agreement with how we determine the GTN parameters. Thereafter, so we would have the simulations with unloadings too. We made this version 2. This way we were able to analyze the data based on the ASTM E1800-2020 standard. Here the tests were done with around 40% unloadings, but when we analyzed the data, we used the recommendations stated in the standard. So here in the table, we can see the track extension and the G integral values which were determined from the standard or in case of the test, and also in case of the simulation. The simulation is a little bit under determined the result, but they are quite good agreement in our opinion. But to make it a little bit faster, because these were 3D simulations, we wanted to use the VCCT simulation method, where we made some changes. Basically, the first version of VCCT is energy-based. We have to have the energy value, which is based on the fracture toughness, and the crack would propagate. We changed this method, and the idea was is not to use the energy values, but for the driving force to use the critical failure values determined the GTN method. So the two methods was combined together. This way the crack could propagate as the mesh opens up, and all of the J integral to be calculated continuously during the simulation. Also in this case, we made two simulations, one without unloading. Here we can determine the G integral directly from the simulation, and the second one with unloading. So the same way it could be generated, the G integral like previously with the standard. Thereafter, we compared these results with the test, and they were quite good agreement. There are two different initial crack lengths, as can be seen, but in both cases, the simulations and the testing results were going together. And to summarize our results, I would like to say a few words about what were the fracture toughness values we obtained. In the first three cases, we used the evaluation of the standard. It can be seen that they are quite in good agreement. In the fourth case, where there was only the simulation without unloading, the fracture toughness was very close to the tested values. The difference was only 2.4%, and because there is an uncertainty in the determination of the fracture toughness, it is a well acceptable value. So to summarize our results, we made article neutral network to use the GTN parameters generated from them. The parameters were validated with CT specimens. Thereafter, we compared them with the testing results where we used unloadings. And finally, the VCCT model was updated with the GTN method, and they were combined so it could be analyzed without the fracture toughness result, how the crack would be propagating. This method is less time consuming, and it estimates well the crack propagation and the J integral values, because the mesh open up with the propagation, and also it continuously can calculate this way the J integral. We think that this method could be applied later for large-scale specimens, large-scale components, and also small-scale miniaturized specimens. And thank you very much for your attention. And also I would like to say thanks for the Fractezos project, because this is a preliminary calculations done for this, because here the miniaturized specimens are the topic.